This exercise related to electric field and the capacitor. We'll do question 22 and 23 today. In question 22, a capacitor can be charged and discharged using the following circuit. It can be assumed that the ammeter has a zero resistance. Initially, the switch makes a contact X and calculate the charge stored by the capacitor as it is when it is fully charged. So when a capacitor is fully charged, we have the formula Q equals CV. When the capacitor is fully charged, the voltage across the battery will be same as the voltage across the capacitor. So if we need Q, the total charge, that is C times V. So C is the capacitance, which is 680 nanofarad, 10 to the power minus 9. And V is the voltage, that is 1.5. So 680 exponent minus 9 times 1.5. So we got 1.02 exponent minus 6 coulomb. That's the charge stored on the capacitor. The switch is moved to make contact at Y so that the fully charged capacitor is discharged through a resistor of 220 ohm. Calculate the charge remaining on the capacitor after it has been discharged for 1 millisecond. Comment on your answer. So this is the maximum value of the charge which we got the previous answer. Now we want to find the charge after 1 millisecond. So we can use the formula that Q equals Q naught e raised to power minus T over RC. Q equals Q naught e raised to power minus T over RC, where Q naught is a maximum charge there on the capacitor, the maximum value of the charge, which we calculated in the previous one, that is 1.02 exponent minus 6 e raised to power minus T, the time 1 millisecond is there, so it will be 1 into 10 to the power minus 3 divided by R, the resistor through which it discharged 220, and the capacitance of the capacitor is 680 nanofarad, so minus 9. We just have to simplify this. So what are the value for Q? It will be 1.25 into 10 to the power minus 9 coulomb. And we can compare this value with the original value. The original value is 1.02 into 10 to the power minus 6 coulomb. And the new value is 1.25 exponent minus 9 coulomb. So we can simply say that a very small percentage of the charge is there that is remaining on the, like we can work out what percentage of the charge is left. As we have the formula, calculate the charge remain on the capacitor. So this is the charge which will be there on the capacitor after 1 millisecond. So we can find the percentage of the charge which is remain on the capacitor, 1.25 into 10 to the power minus 9 divided by 1.02 into 10 to the power minus 6 into 100. That will give us what percentage of the charge left on the capacitor. In part C, the capacitor is charged and discharged 500 times per second. Calculate the average current. So if we need the current is charge divided by time. And reciprocal of the time is a frequency. So we can also say I is equals to Q into F. The frequency here it's given 500 times per second. And what is the charge whenever it is charging or discharging, how much charge is there? That is the maximum value because the capacitor is charged and discharged 500 times per second. So if we assume that the maximum charge is going out, so this Q will take the maximum value of the charge. which was there on the capacitor, that is 1.02 into 10 to the power minus 6, times the frequency, which is 500 hertz. When we multiply, we got 5.1 into 10 to the power minus 4 ampere. That's the maximum charge. That's the maximum current, which will, or average current, which will flow through the ammeter. Question 23. A student was investigating the charge and discharge of a capacitor. When we close the switch, the conventional current move and the capacitor will store the, we don't say capacitor stored the charge, we say capacitor stored electrical energy. Why we don't say capacitor store electrical charge? Because if it is plus 3 and minus 3, so the net charge will be 0. That's why we always say the capacitor store electrical energy. So calculate the time constant for the circuit. Time constant is actually a product of resistance and the capacitance. So the resistance here is 1.5 kilo ohm, which is 1.5 exponent 3. And the capacitance is 200 microfarad. This is assignment related to electric field and the capacitor. So C is the capacitance, which is 200 microfarad. So it will be 200 into 10 to the power minus 6. When we multiply them, we get the time constant, the value of a time constant, because time constant is a product of resistance and the capacitance. So it means 0.3 seconds. So what is the significance of the time constant? Time constant is actually, it's a time taken by capacitor to discharge to 37% of its original value, or when it is charging it to reach 63% of its maximum value. That's the significance of a time constant. Like in 0.3 second, the capacitor will discharge to 37% of its maximum value. In part B, we have a student wanted to plot a current time graph as a capacitor charge, but found that the current changed too rapidly for him to take the reading. Instead, he modeled the experiment using a spreadsheet, and the switch was closed at time t is equals to 0, and V is the potential difference across the capacitor. So certain time intervals are there, and the change in the difference and the potential is also shown. How the value of a B5 is calculated? Cell B5. So what is cell B5? This is cell B5. How this cell B5 is calculated, or how we got the value of this? So if you want the value for B5, means the current, the maximum current. So what is the current? Current is voltage divided by, we have the formula V equals IR. So if we need I, it will be V over R. So voltage divided by resistance, we will get the current. So that is one way of doing. There's all like the second way, the second method, it can be, if we need the current is charge divided by time, like rate of flow of the charge and divided by time interval, we can also find the current. Both ways can be used. Now we check cell. The maximum voltage of the, because what was happening here in the circuit, when time t is equals to 0, the maximum voltage is 6. So means when we close this, the moment we close the switch, the maximum current will flow. The ammeter reading will be maximum. But as the capacitor voltage start to increase, like example, if it is 0.1, the current will flow. 0.2 current will flow. Eventually, the voltage of the capacitor is same as the voltage of the supply. Then the capacitor will stop charging, like capacitor will not charge. And what is the current here? The value of the current, it will be 0 ampere. Means there will be no current flow in the circuit, so it will be 0 ampere. So you can see from the table that at the beginning when the current was zero, when the time was zero, the current was 4 milliampere, the maximum current was there, and the change in the charge was 400 and the voltage was 2. Then after zero point 0.1 second, the change in the charge was 267. The total, like every second, the charge. So this is a supply. We close the switch. We have a resistor and we have a capacitor. So first the charge will enter. How much charge enter? 400 coulomb enter. And how much time it took? It took, because it's a flow. So in the beginning it is 400. Then after 0.1 second, how much charge enter? 267 enter. So the total will become 667. Then after another 0.2 second, how much charge enter? 178. So 178 enter, the total will become 844. Then after another 0.1 second, the interval, 119 coulomb of a charge enter. So the total charge will be 963. So we got different charge. And why the amount of a charge which flow through the capacitor is decreasing? Because the capacitor voltage is increasing. In the beginning, it is having a smaller voltage because it was uncharged. But eventually what will happen when the total voltage here across the resistor and the capacitor, like here, if we have 5.93, as you can see, if we have 5.93 volts here and we have, let's say 0.07 volts here, so the total will be 6 across this one and the battery is also 6, then the capacitor will stop charging. Capacitor will not charge because now the total voltage of the total EMF is equals to total potential difference. So in the question, we want to find how we calculated cell B5, means the current. So how B5 is calculated? That is what we want to figure it out. So how we calculated? So we know the current is voltage divided by resistance. How much will be the voltage across the resistor? How we know what is the voltage across the resistor? Because if we have, say, a supply is there 6 volt, a resistor is there, a capacitor is there, and an ammeter. So this is 1.78. If I know the voltage across the capacitor, I can identify what is the voltage because the remaining voltage will be there across the fixed resistor. So at this moment, like, because this is a continuation, so if 3.33 volts here is a voltage across the capacitor, so how much voltage will be across the fixed resistor? So total is 6. But what is the potential difference? So it will be 6 minus 3.33. The voltage here will be 6 minus 3.33. So that will be the voltage across the fixed resistor. And we need the resistance here. We already have a resistance. So what is the value of a resistance? It was given 1.5 kilo ohms, so 1.5 exponent 3. So if I need the current is voltage divided by resistance. So what is the voltage across this capacitor? What is the voltage across this fixed resistor? So it will be 6 minus 3.33 divided by the resistance. So what is the resistance? 1.5 into 10 to the power negative 10 to the power 3. That is how we got the current here. Is it clear how we worked out the current?
Yes, sir.
Okay. Next is some of the data from a spreadsheet has been plotted on the graph, the current I against the time. Plot the missing points and draw a line of a best fit. So what you have to do, because here you have I and T, which is in millisecond, and here we have I as well. So using a spreadsheet, these values are there which are plotted. Yeah, we just have to check which point is not there, and then we have to draw a line of a best fit after working out those points. So this will be the line of a best fit. Next is the time constant. How to work out the time? Use the graph, determine the second value of a time constant. How we can determine the time constant? We have the formula I is equals to I naught e raised to power minus t over RC. This product of RC, what we call the product of RC, is known as the time constant. And time constant is also when it is discharging, like when, because the charging and the discharging current is always same graph. Even a capacitor is charging or discharging, the value of the current will always decrease. Like it will start with a maximum and it will decrease, even it's charging or discharging. So maximum value is I naught. What is the time constant? The time constant is the time taken by capacitor to discharge to 37% of its original value. So that is when we reach 37% of original value, that time is called time constant. So how we can figure out the time constant from our graph? So the maximum value is 4 milliampere. So leave milli, just take 4. So what? So then we'll work out the 37% of the 4. So what is the 37% of 4? 4 into 37 divided by 100. What's the answer? 4 into 37 divided by 100. 4 into 37 divided by 100 means 0.37 divided multiplied by 4, which is equivalent to 0.37 times 4. And we already have these values. 0.37. So 0.37 times 4 was 1.48. So when we worked out this, so 1.48, 10 boxes equals to 1. So each is 0.1. So 1.1, 1.2, 1.3, 1.4, and 1.48 somewhat here. So when we draw a line, we got this time, and 10 boxes equals to 0.2. So each is 0.02. So 2.22, 2.24, 2.26, 2.28. Or about in the same range, we will get around 2. So this is 2.27 we'll get. So 2.27 will be the value for the time constant. Is it clear, this one? How we know a line of a best fit or a curve we have to draw? It is a charging and a discharging. So it's always an exponential graph is there. So it's always a curve. If it was an ln versus t, if it was ln versus t, then it will be a straight line. But if it is I versus t, then it will be a curve, exponential change. Same thing if it is a voltage and current graph for a capacitor, it will be a curve. But if it was ln v over n t, then it will be a straight line. So charging and discharging of capacitor is always a curve, exponential change. Suggest how student might change his spreadsheet to give more accurate model of a charging of a capacitor. The best way whenever we want to improve, because it's a curve, it's hard to like have a more precise answer with the curve. Then what we student can do, student can plot a graph between ln and t, because ln and t should be a straight line. So when the points were there, we can draw a line of, we should repeat the like have more values, more sets of result, and instead of plotting a graph between I and t, we'll plot a graph between L and I and t. Why L and I we choose? Because L and I and t graph is a straight line, so we can identify the anomalous results. But in a curve, it's hard to identify that which result is wrong. Like when you have a curve, it's hard to recognize like which point is wrong. But when you have a straight line graph, we can easily identify that which point does not appear in the range. So you can neglect that point. So if whenever we want to repeat, like improve the experiment for charging or discharging current or voltage or a charge for the capacitor, we should plot a graph between ln I and t, or we plot a graph between ln V and t, or plot a graph between ln Q and t. And when we plot a graph between ln I and t, so when we plot a graph between ln I and t, so what will the gradient? We have the formula that I is equals to I naught e raised to power minus t over RC. So when we take ln both sides, so ln I is equals to ln I naught e raised to power minus t over RC. So this will be ln I naught plus ln E minus t over RC. ln and E will cancel out, so ln I is equals to ln I naught minus t over RC. If we rearrange the equation, I can say ln I is equals to minus t over RC is plus ln I naught. Now, if I compare with the equation of a straight line, so y is equals to mx plus c. So on y-axis, if I have ln I, on y-axis I have ln I, on x-axis I have t, the time. What will be the gradient? So the gradient will be minus 1 over RC, which is RC is actually a time constant. So if I need a RC, so it will be reciprocal of the gradient. So it will be much more easy. Instead of plotting a graph between I and t, we make a graph between ln I and t, because it will be a straight line. So we can recognize the anomalous results, the point which does not lie in the range. And when we work out the gradient of that graph, directly we'll know the time constant. ln and E are anti-functions. It's like same thing. If I say something is multiplied and divided by 2, it is the same. The multiplication and division are anti-function of each other. Same thing, ln and E are anti-function. So ln and E, they cancel out each other. The mathematical function ln and E are anti-function. Like plus and minus anti-function. Multiplication, division, anti-function. So same thing, ln and E, they cancel out each other, turn out to be only the quantity. So if I have ln Ex, so ln Ex is actually equals to x. This is because these two cancel out each other. So this is a mathematical equation. You have to understand the concept of ln. Remember, if it is ln, the function ln, if it is ln A and B, it will become ln A plus ln B. If it is ln e raised to power A, it will turn out to be A only. So we were having the equation I equals I naught e raised to power minus t over RC. So we take ln both sides. So this will become ln I, and this will become ln I naught e raised to power minus t over RC. Because these two quantities are multiplied, whenever two quantities are multiplied, it's written in addition in ln. So this will be ln I, and this will be ln I naught plus ln e raised to power minus t over RC. Then ln and E cancel out. So we have this ln I is equals to ln I naught minus t over RC, because ln and E cancel out. Just we rearrange the equation. So we wrote ln I is equals to minus t over RC plus ln I naught. Then we compare with the equation of straight line, which is y equal mx plus c. So on y-axis, if I take ln I, on x-axis, if I take t, what will be the gradient? What is left is a gradient. So it is minus 1 over RC is the gradient. So minus 1 over RC will be the gradient. And what about the y-intercept? When we take a y-intercept of this graph, so the y-intercept will be equals to ln I naught. So this is how the logarithm function for work, the ln. Next is an alternative method of finding a time constant is use straight line graph. State and explain the variable that the student should plot and how he should determine the time constant. So suggest how student might change his spreadsheet to give more accurate model. Like what he should do, he should this point was like he should repeat the experiment for more time intervals, and then how he alternative method is there in which we make a straight line graph. This just we just discussed now that you should plot a graph between L and I and T. Is it clear?